All right, so let's first talk about the standing wave with two fixed ends. So we basically have three choices here. If I'm sending a wave back and forth, I've got two fixed ends.
That's not the one, not this one. Okay.
I have two fixed ends. I've got one fixed, one free, and then two free ends. So those are basically the three things that we're going to be testing out here. Two fixed ends, we're going to have what's called a string vibrator, and we'll be using that. One fixed, one free. We'll have these long sound tubes, and so I'll grab that prop in a moment. And then two free ends, we'll have an open tube. So this is going to be an open tube. This will be the sound tubes. And this will be the string vibrator. All right, so we're sending a wave back and forth. So for the two fixed ends, the simplest pattern looks like that. I've got I have a node here, I have a node here, and I have an antinode. This is known as the first harmonic. If I make the distance from here to here, the distance between them is L. A question in doing analyses is, what is the wavelength? Remember, a wavelength is how far a wave travels in one period. So the time it takes me to move out, back, and then back to where I started, going in the same direction, that's the period. How far does it actually travel? Well, a wave, a full wave, looks like that. That's a full wave right there. Because that's the time it takes for me to move from one direction all the way to the other direction and then back to the starting point. If that were a standing wave, it would look like that, with three nodes and two antinodes. So if this is a full wave, how many waves is that? Yes. So L, that length, is a half of a wave. So the symbol for a wavelength. And so the wavelength would just be 2 times whatever that length is. The second harmonic well, every time you add a harmonic, you basically are adding half a wave. Or adding an antinode and a node. How many waves is this?
1.
So L is equal to the wavelength, or the wavelength is equal to L. The third harmonic. I'm going to write it as the improper fraction, 3 halves of the wavelength, or the wavelength is 2/3 L. And so on. Every time L is equal to an extra half of a wavelength. All right, let's talk about the speed of the wave. We did notice that as I tightened it up, it went faster, but before we get to that, there's basically 2 formulas for speed, and from an experimental point of view, we'll equate them, but for right now, let's just talk about speed of a wave, or more specifically, think back to chapter 3. What was the formula for speed?
distance over time.
Yep. And if we think about one period, maybe I did this last on a couple days ago. If we think about the time it takes to do one period, the distance it travels is the wavelength, the time is a period. But period is just the reciprocal of the frequency, so we get this equation. So we know that whatever the speed of the wave is, it's the frequency times the wavelength. So we timed how long it took me to move my hand back and forth. We would have the period, so we could find the frequency. The wavelength would be based upon the distance between Ellie and myself. And we can figure out how fast the wave was traveling. Equally, so this is going to be true for any wave. Now, there is another generic formula for speeds of waves. And there's some sort of force term over some inertial term. The force term is as one part of the wave, as one part of the medium moves, how much force does it apply to the thing next to it? In the case of this, that would be the tension. The inertial term is, in essence, how much mass are we trying to move? The more mass, the harder it is to move. So that's a generic equation that actually works across the board, regardless of how many dimensions and what type of wave it is. But specifically for a line, or something that can be approximated as a line, so V for a linear medium, that's equal to the tension divided by the linear density. So, I mean, someone in here has done this before. What is the formula for density? In general, think back to physical science. Presumably you had it in that.
Mass divided by volume.
Yes. So density is mass divided by volume. Density. The symbol used is a rho, and that is mass divided by volume. What's approximately the density of a human? Any of you ever floated on the surface of the water? None of you have floated before? Okay, we have one. How do you get yourself to sink? Oh, you didn't do that?
It's hard to explain. I guess you just
You push up, wrap around.
No, without pushing with your hands.
Push the air out of it.
You exhale.
Yeah, you exhale. So I know that I will float like this, and I will sink like this. That's not a lot of difference in volume. So my density is roughly the density of water. We are composed primarily of a whole lot of liquid, and so our density is roughly 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. Anyway, density, mass over volume. Surface density since we're not dealing with, so that's sigma, that's the symbol for surface density. There are others that are used, but that's the one that I use. is mass divided by area, because surfaces have an area, they don't have a volume. And then there's linear density. You want to take a shot at that one?
Mass of divided by length of the rock.
Yeah, mass over length. There had to be some mass term in there somewhere, because it's an inertial term and mass is a measure of inertia. All right, so we have a speed of a wave that's equal to the tension divided by this linear density, so we could, if we plugged in our formula for mu, the speed of a wave in a linear medium would be the tension divided by mass over length, or the square root of tension times length over mass. It depends upon your mood. And I am going to change this L to a different one. Sort of the cursive lowercase. Because this length right here is not the same as this length right here. This length right here is the distance between the outer two nodes. This length right here is the length of whatever you've just found the mass of. So what I'm going to do right now is I'm going to go get some props. We're going to come back and see how close we can actually get to predicting the frequency of a wave with two fixed ends. Go ahead and pause this and hope to remember to start back up again. Then it works perfectly. All right, the first thing is we need a string, and we need to figure out we need to measure the length. There's a meter stick. And that's probably enough. Oh, thank you. And I just had the scissors in my hand, and I put them down here. There we go. All right, so let's find the mass of it. Now, I've noticed I've had students do this lab quite a bit, and I noticed that a big issue comes in finding the mass, because the mass is so little here that if you're a little bit off, it can have dramatic consequences. So first, is it on 0 when I first begin? It's not. So I'm just going to cheat it up a little bit. And I noticed that it was having issues there. As a hub. So what I'm trying to do is figure out what is the mass when there's nothing on it, and I'll subtract that from whatever this mass is. And just to give us some running room, I'll just do it here. Put all that. Oop, too far. All right, and to me, it looks like it is pretty well on there. A little bit. All right, so with nothing on it, it is just shy of 0.3 grams. I would estimate 0.28. Just in my hand. All right, so the mass with nothing, 0.28 grams. So now I'm going to put this on there. And figure out what the new mass is. All right, and with the string on it, it is 1.73 grams. So therefore, the mass of just the string is
1.45.
all right.
Great.
Now, it might not seem like much, but if we had not done this piece right here, we would already have introduced a 14% error. Now we need to figure out the length, because we're trying to get that linear density. And we conveniently have a meter stick here. Now, sometimes the ropes will stretch some. This one doesn't seem to be stretching much. Go on. All right, that's 1 meter to there. Uh, 198.4 centimeters. Length, 198.4 centimeters. Centimeters. In order to make life easier, let's get them into the SI terms. So how many meters would this be? Louder?
0.1984 meters.
1.9.
Yeah. Centimeters to meters, 2 decimal places. Yeah, 0.198 meters is about that long. All right, and then let's get the mass into kilograms.
Three decimal places.
Say it again.
3 decimal places.
You said 3? So 0.00145 kilograms. Oops, sorry, that's the way. And so therefore, the linear density of this string is the mass divided by length, which is 0.00145 divided by 1.984, and that's kilograms, and that's meters.
Zero 0.00073 058.
Is that right? Did I write that number correctly?
Oh, 85.
85.
85.
So you get something different?
Uh-huh.
What'd you get?
I got 7255 in there.
You got 7255.
Uh-huh. Oh no, she was right. That's me.
No. So 0.0073085.
Yeah.
All right, units?
Kilogram per meters.
Yes, just right there, kilograms per meter. So kilograms over meters. All right, that is a 0 there. So we have a linear density, so now if we know what the tension is, we can figure out how fast it should be moving. And so that's when we bring in the string vibrator. Table's not necessarily conducive to this, but you know what, we'll give it a go. Now, as you add tension to it, the the more tension on the string, the lower the harmonic will be. And when I was recording the video, when we went into lockdown, I had a video lab basically for this. And I thought, well, let's just get a really long string so that it's easier to get the higher harmonics. Because if you have a really short string, it's really difficult to get, say, the 6th harmonic or 7th harmonic. So I had a really long one, but the really long string required much more weight added to it in order to get the tension. And that string broke, and the pulley came off the rod, et cetera, et cetera. I had to cut out more profanity from that video than any other video I've done. But one of the issues that I did not have to deal with was sometimes there's so much tension on it that these things start to move. And so we bring the C-clamp and we tighten it down. And I've got the rod there. Oh, no, actually, I should be able to handle this. Okay. There. It won't hurt. Unless it snaps and then goes slinging back. What generally happens if the rope breaks or the string breaks is that there's a big thud as it lands. All right, so first off, the string vibrator here